Hi everybody, this video starts the beginning of section 2 of chapter 6, and here we will talk about the standard normal distribution. This distribution is not normal, it is also standard. It is essentially the distribution that covers z-scores. So basically the standard normal distribution is the distribution you get when you convert your Gaussian values to the equivalent z-score. And what we're going to do is we are going to compute the probability of certain z-scores occurring. And as I mentioned before, when you have a normal distribution, the probabilities are determined by the area under the curve. So we're going to go over how to compute the area to the left of the z-score if your outcome is less than a particular number, to the right of a z-score, which is the case where your outcome is greater than a particular z-score, and between two z-scores when your output is between the probability that your output is between two different values. Before we can do that, we need to talk about what the standard normal distribution is. And I kind of touched on it in the last video. But let's start off with this. This is your normal distribution. And we talked about this. It is centered at the mean. And it's also symmetric about the mean. And it has points of inflection at the variance. Not the variance, but points of inflection at a distance of a standard deviation away from the mean. Okay, and this gives you the graph of a normal distribution with a mean of mu, whatever that happens to be. Well, the standard normal distribution is nothing more than x for the case where the mean happens to be 0 and the standard deviation happens to be 1. And this is the distribution associated with your z-scores. So when you compute a z-score, what you're doing is you're taking a point from here and you are finding the equivalent point here. Why is that useful? Because we have lots and lots of tools that will help you compute probabilities for this point and for a variety of other points. Okay, as you mentioned before, normal distribution is symmetric about the mean. Its standard deviation, of course, is sigma. The area under the curve is always 1. The asymptote is always the x-axis, and the values of the distributions we tend to call x-scores. For the standard normal, mean happens to be 0. It's symmetric about 0. The standard deviation is 1. The area under the curve is always the same. The asymptote, horizontal asymptote, obviously is the same. And the points on the graph are what we call z-scores. When I say standard score or z-score, I'm looking for a point on the standard normal distribution. Okay, so let's let x be any point on a normal distribution with a mean of mu and a standard deviation of sigma. Okay, well then we know how to compute a z-score. We did this at the end of chapter 3, and this is how we do it. Okay, if that's the case, then it turns out that z is equivalent to x in the sense that the probability that x is less than or equal to x was going to be equal to the probability that the random variable z is less than or equal to z. So if you want to figure out that the probability of x being less than to a certain number, find the z-score and compute the probability that z is less than that particular number. You have your answer. And we are going to spend the rest of this section focusing on this. Okay, so here is our first example. And this is just an arbitrary example. Let's suppose that x is a normal distribution. The random variable x has a normal distribution with a mean of 50, so here's 50, and a standard deviation of 5. So basically their points of inflection is 1 standard deviation above it, 55, 1 standard deviation below it. And let's let x be 47. Well, the equivalent z-score here is minus 0.6. And there's that particular point in the graph. Now these aren't exactly the correct graphs, but they've been scaled just for visual purposes. And notice that the point here is pretty much similar to the point here. The area below it is pretty much is identical to the area below it and above it and so forth. So the probability that x is less than or equal to x is the same as the probability of z being less than or equal to the number z. I should say that the probability of the random variable x, this random variable, is less than or equal to our number x, which happens to be 47, is equal to the probability of this random variable z is less than or equal to the number z, which in this case is negative 0.6. And this brings us to our first example. Here we want to find the area under the curve, under the standard normal curve that is to the left of z equals 1.37. Now, in Hawks, you're going to find a whole bunch of tables that you can use, and in your homework they're going to make certain tables available to you. This is one of them. This is the normal table from negative infinity to z. This right here will provide for you the area under this curve for all z values down to the second decimal place. Okay, so if you want to find the area to the left of 1.37, you go to this table. Okay, you look up 1.37, and this is how you do it. You go over here, and you want to use this for your single unit and your first decimal, 1.3. Okay, and then you want to walk over, and this right here is your second decimal. Then you want to walk over to 1.37, and there it is. Your answer is going to be 0.9147. That is actually the answer that you're going to want to put into Hawks. Now let's just take a quick look at this table. Notice here that we start with z is equal to 0. That's this line that's this vertical line right here. Notice that the area to the left of 0 is always going to be equal to 1/2 in a standard normal, which would make sense. And also notice that the values are always increasing. They are always monotonically increasing, which kind of makes sense because what you're doing is you're moving x this way and you're accumulating area. So this starts at 0.5. It is always monotonically increasing, which will come in handy for the cases where I give you an area and you need to figure out the associated z-score. But heck, I believe that is section 4, not section 2. So we will worry about that then. Okay, and here's another one. Here we want to find the area under the standard normal curve to the left of z equals negative 2.55. Now for this one, we're going to use a different table. It is a normal table from negative infinity to negative z. Now once again, the column here will provide is what we're going to use to look up the single unit and the first decimal of the z-score. Notice here we have negative 2.5, negative 2.5. Now also notice that unlike our previous table here, where we go from 0, we start off for the second decimal place, we start off with 0.00, 0.01, 0.02. This one does it backwards. 0.09, 0.08, 0.07, 0.06, 0.05, and so forth. So we want to start off at 0.09 and go down to 0.05, and this will be your answer. Okay. Also notice that these entries are monotonically increasing. We start all the way down to, I believe, almost like -5, which I believe is obviously going to be 0, and we increase in this direction, which is also why this is why this counts down the way that it does. But nonetheless, our answer here is going to be 0.054. So this is how you can find areas to the left of a curve, basically using the tables that you will find in Hawks. And you might find this an easier way to do it because all you have to do is look up the value, click on this, it loads the answer field, click OK, and you're good to go. You can also do this using technology. And I know I have all this stuff here, but I'm going to walk through it using my handy dandy, where is it? There it is, calculator. There she blows. So let's go ahead and take a look at this, and I'm going to cover all this stuff up so it doesn't look too confusing. All right, and I want to go to my simpler calculator. That is this one. Okay, now to do this, we are going to go into distribution. Okay, so second VARS, and we are looking at a normal CDF. Normal CDF is that function which will produce for you area under a curve. So we're going to go highlight that, hit enter. Okay, my lower is 1e to the negative 1e to the 99. That is basically a negative 1 followed by 99 zeros. That's the smallest value this calculator can produce. So that's their equivalent of negative infinity. Just go ahead and hit enter. The upper value, 1.37. Okay, we're dealing with a standard normal, so the mean will be 0. The standard deviation will be 1. Hit paste. Hit paste again, and here's our answer, 0.9146, and my next decimal place is 5, so we will probably need to round my 0.9146 to 0.9147, and that really is all there is to it. And there we go, once again, 0.9147. The other one's done the exact same way. Here, I can go back into distribution again, or I could go ahead and use my history. Click on that, hit enter, and all I will need to do here is change the 1.37 to negative, this negative right here, 2.5, and now I need to insert because this thing does not overwrite, this overwrites 0.5. 0.1, and that will give me 0.00538. Now, to do this using the do this in the previous way, because that might be easier for this type of calculator. Second, distribution, we want 2 normal CDF, and then we are just going to change the 1.37 to negative 2.55. Mean is 0, variance is 1. Paste. And once again, we get 0.00538, which will round to 0.0054. And that is all that we are going to do for this particular video. Stay tuned for a follow-on video where we will talk about how to compute the areas to the right of the z-value and how we compute the areas between the z-values. If you have any questions, please feel free to contact me. This is Bob Boyle, signing off.